All right, so welcome in. So here are two examples that I want to take a look at, and you'll see that as soon as you attach a rope, let's say to a box or to anything that you want to be able to pull across the floor, and you now have that particular rope and you start changing the angle of the rope. So as you can see there on the left hand side I have a box and basically the rope is horizontal, and then on the right hand side I have a box and the rope that I'm going to be pulling on is at a 30-degree angle. Now the angle doesn't matter, but the reason why I bring this up is because it's a very interesting question to break down your forces and then what actually happens. Now, when there's really no friction, the problem is a little bit easier to tackle. But here I'm going to assume that there is friction. So you'll notice that the box itself has a mass of 10 kilograms and that I have a static friction, okay, which is 0.25. So that static friction, you may recall, is dependent on the actual maximum friction, right, that you can have before the box moves. Now I'm going to put up a link up above there and you can take a look at static friction versus kinetic friction if you wanted to. And in this example, the goal will be to ask the question, what is the maximum amount of tension, okay, that I can place, that I can basically be pulling these things, okay, right here, so that the box still remains stationary. So just before it actually moves. So there's no movement. So notice I have F net is equal to 0. So that's going to be my assumption. And what's interesting is that the maximum amount of tension that you can put in here will depend on actually the angle that you're going to be pulling in. So now we're going to be assuming that the angle is, okay, towards the horizontal. So it's kind of up. What happens? You obviously don't want it at 90 because you're not going to be pulling it anywhere. But in any case, so let's take a look at these two separate conditions. So the goal will be to find the maximum tension that we have so that the box still remains stationary. Now, the only way that that can work is that there is friction, right? So that's why I said, if there is no friction at all, then obviously the box will start to move no matter what force you apply to it. But if there is friction, you have to break this static friction before the box actually starts to move. So let's take a look at how this would actually work. So I'm going to take the example on the left first, which is the easier example because we don't have an angle, so at least the angle is 0. So here I am basically trying to pull this in this direction. So if I have that the F net is equal to 0, so my net external force is equal to 0, then this is what I'm going to be running into. If I take this box, okay, so I'm going to take this along, I'm going to duplicate it, bring it down here. I'm going to just draw a free body diagram with regards to all of the different forces, okay, that I would have. So here's my one force. So this is going to be my force of tension that I would have, that I'm going to be pulling. Here is going to be the force of friction. Now this is going to be the force of static friction, okay, that I have. I'll call this F and little s for static. Now I cannot forget that I still have, my force of gravity, which is going to be trying to pull this down. And of course I have my normal force, okay, which is going to be upwards. Okay, this is going to be my Fn, or just capital N if your teachers use that. So that's my free body diagram that I have in here. Now I know that my net external force is equal to 0. So this box isn't really moving. So if you consider this and the box isn't moving, so let's say in the y direction, well, if there is no movement, then I know that in the y direction, my F net is equal to 0. So this is in the y direction, so it's equal to 0, which therefore means, so if I'm assuming that up is positive, so Fn minus Fg is going to be equal to 0, or simply that my normal force is equal to my force of gravity. Now, why this is important is because of the fact that we do have friction. And if you recall, so from friction, so what we have is that this actual coefficient of friction is equal to nothing else but the actual maximum force that you can apply before the object starts to move divided by the normal force. And of course, what that means is that this particular force of friction, what it would mean is that it's going to be just the coefficient of friction multiplied by the normal force. And that's going to be my static friction, right, that I will have. And my tension is going to have to balance that off before, this object starts to move. So this is important for us right there. But that is in the horizontal direction. Now, here, okay, this normal force, it's important because notice that it is, okay, applied in here, and it does have an impact on my horizontal right there. So now if I break this down and I take my x direction, so I still know that my net force in the x direction is equal to 0. So this is what I have right there. Now in the x direction, so again, I'm going to assume that right is positive. So I'm going to have my force of tension minus, okay, this force of friction. And again, so what this would mean is that the force of tension has to equal to the force of friction. And this is nothing else but simply just your coefficient of friction times your normal force. But my normal force, as you can see right above there, so my normal force is equal to the force of gravity, which is going to be just mass times gravity. And of course, I can substitute that back in here. And what this would be, so that means that my static friction, okay, is going to be, so this is 0.25. My normal force, which is just mass times gravity, this is going to be 10 kilograms multiplied by 9.8, right? So this is the gravity, or 9.81, whichever one that you use. And I can now calculate this through. So what would this be? So if I take this 0.25 times 10 times 9.8, and that is 24.5 newtons. I'm going to forget the rounding in here. So let's just keep it as it is, okay, and not worry about the rounding. The actual interpretation of this matters to me. So what does that mean? What that means is that my force of tension, this is the maximum force of tension that I can apply. So that would be right here, so that it balances off, okay, the static force of friction. Because if I apply more, it will now make the actual object move, or this box move to the right, if I'm going to be applying more. So I cannot apply more than this. And now notice that what I had, this was all in the horizontal, right? So because I'm pulling right in the horizontal, and this is how you can break this whole thing down. Great. So now let's take a look. So if I have all of this information in here, let's try to see how this would compare. So all of this, how this would compare. I'm going to make this a little bit smaller in here. How it would compare to the right-hand side, what actually changes. And this is where students will have difficulties because of the fact that now all of a sudden you have an angle. So your force of tension, so now that we will take this, I'm going to take this, duplicate it, and let's draw the free body diagram in here. Okay, so let's say I have that. Now, what do I have in here? Well, so here is, if I'm going to be putting in, this is going to be at 30 degrees. This is now my force of tension. Now, this particular force of tension, okay, is going to have two components. It's going to have an x component, and it's going to have a y component right there. So those are my two components. Now, I know that the angle there is 30 degrees. So what this would mean is that my y component, so this is just from trigonometry right there and triangles, so this is going to be ft multiplied by the sine, okay, of the angle, which is going to be 30 degrees. And this is going to be my force of tension, and this is going to be cos of the angle, which is 30 degrees. So those are my two components. So this component is really, that's the magnitude of it, and this is the magnitude of the y. Notice that it's in the up direction. Now, why does that matter for us? It matters now because of the fact that you have now both a horizontal and a vertical component coming in from the tension. And you can think about this as, if you're going to be pulling at an angle, your actual object, so this particular object that you have, so this one right there, the force of gravity that you have, well, if you're going to be pulling a little bit up, with some of the tension, so it's going to be almost like lifting up the object, that will have an impact on your normal force right there. And this is why this is important. So you can't really neglect this, right, unless your teachers tell you to neglect this. Now, we're still under the case that the net force is equal to 0. So it's not like the object is being lifted up. It's not, right? It's just basically still staying on the ground. And moreover, it is not sliding across. The static force is going to be preventing that. But this now plays a different role all of a sudden. Because, yes, sure, we still have the force of friction, okay, so within here. So I'll still call it force of friction in here. We still have our force of gravity, so that force of gravity doesn't change. So this is still going to be pulling it down. This is going to be mass times gravity, so that's the same thing. But now we have a normal force as well up here. And you saw that in the previous one, the normal force and the force of gravity were equivalent to each other. And this is most of the time the case. However, this is not always the case. And in this case, it will not be. So let's take a look and break this down. So let's break down the components now. So the y component, well, I still have my net force. Okay, it's still telling me that it's equal to 0. So that's great. However, now I have different items within here. So notice what we have. We have our force of normal, which we do need, by the way, to figure out what the force of friction will be. So we have that. We also have this added feature. Now, this added feature is the component, okay, which is coming in from the actual tension, right, which is upwards. That's going to be this little piece right there. So this is going to be upwards as well. So now, the last piece is, of course, my force of gravity. But this is the extra piece that I didn't have in the previous example right there. So this, all of a sudden, as you can see here, if you rearrange this, this is going to be your force of normal, okay, is going to be, I can take this, and now all of a sudden you're going to get your force of gravity minus the force of tension times your sine, okay, of whatever angle that you're dealing with. So notice that it is subtracting, right? It's subtracting from the force of gravity, and that should make sense to you. The item, okay, is not going to have the same normal force anymore as long as it's 0, right? You're not lifting this thing up. So there you have it. So that's what we have right there. And this is kind of crucial because it's going to be needed for our next item. So our next item, or our next piece, so this is for the x component right there. So what do we have? In our x component, so this is still equal to 0. Now this is equal to 0, well, and you can say, okay, so fine. Well, now I'm going to be dealing with the force of tension, which is going to be cos, okay, of 30. That's what we have in the horizontal, minus the actual static friction force, right? The maximum that is allowable. Now this is all at 0, and now you'll notice that, well, what is this going to be? Because before, notice that our force of tension and force of gravity, so these right here, they were equivalent to each other. Now all of a sudden, okay, what I will have is, okay, so if I put this in here, my force of static friction right there is not going to be the same. So now my force of static friction is equal to this times my normal force, right? Now, if this is my normal force, well, hold on a moment. What I have in here, if I'm going to substitute that back in there, well, that normal force now is force of gravity minus the force of tension, sine of 30 degrees. So there you go. This is what you have. And now all of this, you got to be able to plug this back in here. Now, I know most of these components. I actually just don't know what the force of tension is. Now, once I find out what the force of tension is, I can go back and find out what that maximum static force of friction is. Now, please remember that the force of static friction, right? So it is always dependent, okay, on, so what you have is, this coefficient will not really change, but this force of normal may indeed change, right? So that force of normal changes. So your normal force, okay, is dependent on, is this object just, in this case, how is it being pulled? Because now you're pulling it at an angle in terms of a tension. So now you can see there that it has adjusted. So now substituting all of this junk in here, so I'm going to just take all of this, okay, I'm going to duplicate it back in here. Let's put it down right there, and I'm going to just substitute. So I'm going to get 0 is equal to force of tension. Now I'm going to start plugging these in. So if you remember your unit circle and your coses, if you don't, you can take out your calculator. But cos of 30, well, so this is nothing else. Maybe I'll just adjust this. I'll put the number in front there. Okay, so cos of 30 is going to be square root of 3 over 2. It's going to be ft minus. Now, if I'm going to be substituting this back in here, right? So this is going to be coming from above. So let me just put this in here. So this is going to be 0.25. That's my coefficient of friction. Now, inside of the brackets, this is going to be force times gravity. So this is actually 98. This is coming from the previous one. So notice right here, right? This is F times G. Okay, so that's 98 minus my force of tension, and then sine of 30. Well, sine of 30 is just a half. Okay, so this is what I'm going to have right there. And this is going to simplify quite a bit. Now, when I distribute this across here, distribute this across in here, okay, so this is going to be, 24.5, which was your original one that we had actually all right there, right? This is 0.25 times, your mass times your gravity. Now, the other one, so within here, so this is going to be minus, okay, so within here. So notice this minus right there, okay, so this will cancel this. I'll just leave it like that, just so that you can see the signs. It's going to be minus, and this is going to be 0.25, which is really 1 over 4, so it's a quarter. So it's going to be a quarter times 1.2, okay, so which is going to be 1.8, so this is going to be 0.125 right there. And this is going to be force of tension. And now notice the only unknown is your force of tension in here. So I can group all of this stuff together. Okay, so let me do that, okay, all in one. So that's going to give me now this particular term. So this negative is going to distribute. It's going to make this one positive actually. So this is going to turn positive right there. So what you have is square root of 3, okay, over 2, force of tension, plus 0.125 force of tension, right, minus the 24.5, which I'm going to bring over to the other side. So I can solve for ft. So it's going to be positive right there. And there you have it. So you can, your ft, and now we can do all of this. So it's going to be square root of 3. This is being divided by 2. So equals, that's that. So that's my answer. And then plus 0.125. Now notice it's basically almost 1, which is going to be interesting because now your ft, okay, that you have right there, so 24.5, divided by 0.991, etc., is 24.7, okay, or approximately 24.7, and that would have been your force of tension. So that's pretty neat to be able to see that. Hold on a second. I did all of this work, and it seems that the force of tension is more or less the same, right? Okay, so that's what you would have, okay, in that. And that is what all of this work, okay, actually pretty neatly shows. So what you have in there, okay, is that your force of tension, so within here, so the maximum one, is about 24.7, so it's a little bit more, okay, than it was before. And that was all broken down, okay, for us within here. So now, what is interesting is that the x component is definitely not 24.72, right? So this would have been this multiplied by the cos, okay, of, and that would have been just square root of 3 divided by 2, and this would have been 21.4. That's the horizontal, right, okay, component, and that is your force of friction, which is obviously less. And that should make sense to you because of the fact that you're actually, pulling upwards at an angle. So your force of tension is very close to it, but clearly your force, okay, of friction, your static friction, which is going to be 21.4 approximately, is definitely, less than what it was before there. So there you have it. So that's the maximum, okay, tension that you can hold. All right. So that is it, okay? I hope that these two situations, okay, if you've ever thought about them, what happens, okay, now you'll know more or less how to handle them if you have them, on a quiz or on a test or something else. Okay, thanks for watching. See you in a future video. Bye.